So, Textual Explanation for Self-Driving Vehicles, a paper by Berkeley Deep Drive team. I think the team leader is Trevor Darrell. I'm MD Saifuddin. The main reason of this paper I chose because I was trying to do something with self-driving car. So the research question in this paper can be explained with a picture. Let's say we are traveling on a self-driving car, and suddenly this car starts to slowing down. Then the passengers will think like, what is happening to this car and why it is happening. So the what part can be answered by like watching the slowing down, but the why part can be answered in different ways. Possibility one is there is a stop sign, that's why it's stopping. Maybe there is a right turn coming up, that's why it's slowing. Or maybe there is a vehicle in front, that's why it's stopping. Or maybe the unfortunate reason can be the engine have failed already. Whatever the reason, knowing the actual behavior of the car is important because the self-driving car is a new technology and nobody trusts it yet. So it's important for everyone to know that the vehicle is doing something for a specific reason. Another thing is whoever uses this car, they need to understand their vehicle behavior, whether there is any problem or any error in the behavior of their vehicle. And another thing is every user may have different preferences for their car. So effective communication with the user is important, and for that explaining the behavior or any action is important equally. So now what way we can know that explanation, like for an action or like slowing down? One can be the rationalization. As human, we do these things, like the car is slowing down, maybe there is a stop sign, that's why it's stopping. But in this case, we do not consider the internal state of this vehicle. So in this paper, author suggested another approach, introspective, which means it will look into the internal state of that vehicle, the action taken by the vehicle, and then it will suggest the explanation of that behavior. For this matter, they use visual attention. Now, in this paper, the authors claim three major contributions. One is they proposed a textual explanation using plain natural language, like vehicle slows down because it is approaching an intersection and the light is red. This type of sentences for human understanding. And another contribution is they have generated a good training data, deep drive data set, and they added human annotation as ground truth. Now, using that human annotation is a little bit tricky because human cannot know the internal states of a vehicle. So that's why the third contribution the authors claim is attention alignment, a new mechanism, novel mechanism to solve this problem. So the main idea on this paper is if we are given some input data in time scale, there will be a controller, vehicle controller, which will predict its acceleration or change of course based on some attention mechanism. And using that output and the attention, the explanation generator will generate a textual description and explanation of the action. The example of the action and description and explanation can be the car is driving forward because there is no other cars on this lane that we see in this picture. So how they do that, how the authors do that in this paper is based on this network architecture. the architecture starts with some input images. It goes through a CNN layer to extract features. The features are used to generate a controller output and some other attention layers. And then it can go either strongly aligned attention layer, attention mechanism to get the textual output here, or it can go to the another approach which is called weakly aligned attention, and it also outputs these textual explanations. So I will explain each of these one by one. First, the preprocessing. Before the input goes through the CNN, it is processed with these things like we will take 4 frames at a time and measure from the sensors, the vehicle sensor, we will measure the acceleration and change of course. And then we will downsample those video data to 10 Hz and resize it to 19 to 116 to 3 images and normalize it. So after that, these downsampled resized images are fed to a convolution layer. The convolution layer consists of 5 CNN layers. They could use other methods, but for simplicity they used, the author used 5 layers. So the 5-layer CNN outputs 3-dimensional feature cube which have 12 into 20 into 64 dimension. So this size, 12 into 20 into 64, this 12 into 20 part is the size of each vector, and 64 is the number of points, the size of the vector. And 12 into 20 is the number of regions it detects.
It's a channel.
Yes, it's a channel. And to keep the spatial information intact, they omitted the max pooling layer. And after that, the XT becomes, each of the vector inside XT becomes a high-level description of a specific region. The convolution layers used here have this type of filters, like first one have 24 filters, kernel size is 5, and they use stride. The first 3 layers use stride, and the last 2 layers didn't use any stride, and the kernel size decreased, and the filter size is 64. Then after getting this feature cube, the activation used is ReLU, and Javier initialization is used on the weights. So using this feature cube, we can go to the controller part. The vehicle controller takes in the feature cube and uses a soft attention mechanism to generate some attention map. Generate this attention maps. So this attention map are then multiplied with the region vectors that we found from XT to generate a context vector YT, which can be explained with this equation. So here, this context, how they got this attention map, the author explained it in this way. The author used controller LSTM, which uses internal hidden state of the previous LSTM and combines it with the current feature cube and gets the alphas. Now, controller LSTM uses FC layer and a spatial softmax and yields normalized attention weights. After getting this YT vector, context vector, then we need to get the output of the controller, which is acceleration and change of course. For this, it uses 2 separate multi-layer FC blocks. Each FC block have 5 layers in it and uses ReLU activation, and the objective function used here is this one. We see the difference in acceleration and change of course, and an additional regularization term which consists the entropy of the attention with the lambda c parameter, hyperparameter. Now we have three outputs from this vehicle controller, YTC and CT and AT. After this, we can go either to the strongly aligned attention part or weakly aligned attention part. The strongly aligned attention part is named after like this because it uses the same attention that we got from the controller part. This attention are used in a consecutive fashion in different times to generate a temporal attention vector, which is then applied with a weight vector beta, and it directly goes to the explanation generator LSTM. So here there is no other attention information generated here, just these attention maps that we got from controller part are used in a consecutive time fashion. That's why they say alpha j, which is attention of justifier, and alpha c, attention of controller, is equal. But in weakly aligned attention, it generates a new attention layer, attention map for each input. How they do that? They got the xt, the feature cube, directly, and it creates this attention map alpha j in the same fashion. To make this alpha j close to the alpha c, there is a Kullback-Leibler divergence loss minimization. This minimization loss is calculated using this formula, where we can see there is a hyperparameter lambda a. So based on this both strongly aligned attention and weakly aligned attention, we got a temporal attention vector or map, which is then applied with this beta weight and goes to the LSTM, which extracts the texts. Now the textual explanation generator. The final state, we can use either the strongly aligned attention, in both cases we have temporal attention. In case of weakly aligned, strongly aligned, we can use the same YT that we got from controller. But in this case, the YT is generated from this alpha j to create a YTJ and used in the textual explanator. So this equation uses also some ground truth of acceleration and change of course, and creates this z vector, which is similar to the YT, but it has this measurement vector concatenated in it. And then a minimization of negative log likelihood done along with the attention loss and controller loss. This minimization, after this minimization, the training part is over, and the network model outputs this type of textual natural language descriptions. So this is one part of the paper. Another part was the authors generated a very good driving data set, which have many human annotation based on Amazon Mechanical Turk, and for the quality testing, the authors saw 72% of the annotation intervals differs in only 3 number. Number of annotation intervals differs less than 3 for 72% of the annotations. And some other modern ways like intersection over union and CIDR score was checked to ensure the quality. And the vocabulary for description part, which means what action the vehicle is taking, is 906, and the justification vocabulary has 1668 words, which is higher. So the data set consists 77 hours of data and almost 26,000 annotations. And some example can be for an input image, this video have 5 parts, 1, 2, 3, 4, 5, and the annotations are like, for first part, the car is driving, and the description explanation is, as there is nothing to impede it. Or if we can go number 4 here, there is a school bus, so it says the car drives in the left lane in order to pass the school bus. This type of very natural, human and understandable languages. So the training, how did the author train this model? The training went with 2 parts. At first, the author trained the controller end-to-end from scratch. And after the training, the controller weights are frozen to train the explanation generator. Optimizer used was Adam, and Java initialization dropout with 0.5. And the data splitted was 80% training, 10% test, and 10% validation. Now comes the evaluation part. After all these things, the evaluation was done also in 2 parts. The first part, the author evaluated the controller output, although this paper is not a controller paper, but it is important to get the controller part right, because the controller attention are used in the explanation part. So for controller part, state-of-the-art method used was Bojarski and Kim. This two-study was modified with identical CNN, and the evaluation matrix used was mean absolute error between this acceleration and change of course. Another evaluation was mean of distance correlation. The author did not put any explanation for this distance correlation, but I think it's the vector distance between these AC vectors, acceleration and change of course vectors. The experiment done to compare effect of prior input, as we saw in the input preprocessing, we used some measurements. In this state-of-the-art study, they did not use the prior input. Another thing was visual attention, as obviously we used visual attention in this paper. And regularization term, that entropy over attention entropy regularization that is used for the controller. So this is the prior input test shows that with prior input, this paper model outperforms the model that is without prior input in both cases, mean of absolute error and mean of distant error. For visual attention, we see adding attention actually improves the result also. This 6.92, although this value is lower better as mean absolute error, it goes down a little. And for mean of distance error, visual attention increases the correlation between ground truth and output data. And for within our proposed method, we see using different lambda c, which is the regularization term, changes the result significantly. As we see, this lambda c has negative effect on the result. That means the attention alignment have negative effect. But, sorry, not attention alignment, it's attention regularization, has negative effect. And the reason behind it is explained with these pictures. See, as we increase the regularization, the attention map becomes sparse. So what happens, as we go to the highest regularization, the attention goes into only one region, and the controller needs to decide based on only this part of the image, which is not fair. But in case of without regularization, there is many things that controller can consider to decide something going right, left, or stop. Now, as the controller performs worse for higher regularization, in the contrary, the explanation part we will see later that will perform better for regularization, because with sparse attention in the pictures, the explanation can pinpoint the reason behind an action. So there is a trade-off between these two. If we go into the explanation generator evaluation, we see the authors used state-of-the-art sequence-to-sequence video-to-text study. In the same way, the CNN was replaced and the optical flow was not used. The evaluation metrics used for this evaluation was BLU, which is bilingual evaluation under study for text. Meteor is a multimodal machine translation evaluation, and CIDR is the consensus-based image description. And also, the authors evaluated the explanation generator with humans from Amazon Mechanical Turk. So the experiment done here compared weakly aligned attention and strongly aligned attention. As we remember the rationalization part without knowing the internal state, they used this part also for comparison, and the regularization term of lambda A and lambda C, attention alignment and controller. So this is the evaluation part. We see BLUE, Meteor, and CIDR are listed here, and explanation and description are evaluated separately. If we go for the state of the art, we see this description part is always better than the explanation part, which is obvious that which is actually expected, because description is always easier than knowing the exact reason. So if we go for any of these study from this paper, like strongly aligned or weakly aligned, all of them does far better than the S2VT. Now, within this strongly aligned and weakly aligned, we see that weakly aligned part outperforms the strongly aligned experiments. The reason behind it, as the author explains, is weakly aligned attention does not use directly the input from controller. So what happens, sometimes the controller attention may not have a human explainable part in it. So for human understanding, creating a newer attention is better, which is compared with the human annotation ground truth. So weakly aligned attention does better than the strongly aligned attention. But luckily, rationalization, which doesn't use any attention alignment, actually does worse than both of them, for BLU, Meteor, and CIDR. But if we go for human attention, human evaluation, we see that regularization somehow does better than the strongly aligned part. That means strongly aligned part may come up with some explanation that human cannot understand. I mean, human, like those explanations are not, doesn't match with the human annotations. So, but in this case, weakly aligned attention does very good than the rationalization part. So overall, weakly aligned attention should be the go-to move to do any attention alignment if we want in future. Some explanation of the evaluation is here. This is the number 5, which shows The human annotator annotated it with car is slowing down in preparation of turn. The rationalization part without internal state, the car slows down because it's turning to the right. And weakly aligned attention, but weakly aligned attention sees this car here, this car, and rightly detect that the car is slowing down because the car in front is moving slowly. So we see that weakly aligned attention somehow manages to see more information in the pictures. So another one can be human annotated it, the car is negotiating a left-hand corner, but the weakly aligned, strongly aligned part said because the traffic is moving at a steady speed, which is wrong. But weakly aligned attention says because it's turning to the left, which is right. So we see somehow strongly aligned attention have more specific knowledge on the environment than the, strongly aligned have worse knowledge, weakly aligned attention have more knowledge about the environment. And we see for the explanation generator weakly aligned, there are less number of attention points, which means they pinpoint the original real region behind the action. This is another result. Here, the rationalization part, which does not look into attention map, actually sees it's parked in the left lane, which is not the right case. Human annotator said it while it waits for traffic in front of it to move. So it was standing in a traffic. Both strongly aligned and weakly aligned detects it rightly because traffic is stopped, because the car in front of it is stopped. So rationalization could not locate any point to look into. That's why it came up with this, as the left part is attended here, maybe that's why it came up with this parking case. But in other case, the controller pinpointed this car, and here the explanation generator also pinpointed this car. That's why it came up with the right reason. So that's all, I think, if there is any question.